Okay, so our next speaker is Moslem Zamani, who is a postdoc at Tilburg University. And let me see what's the title of your talk. He's going to talk about new bounds for quadratic programming. So Moslem, the floor is yours.
Thank you for the introduction. Back in this talk, I'm going to review some bounds for quadratic programming. We consider a general quadratic programming. We are going to minimize a quadratic function, subset of Rn, that this subset is determined by some quadratic and linear, and with lots of generality. This formulation, we assume that X belongs to the unit box. So if the quadratic program accessible set by translation and rescaling, always we can have this kind of concept. As you know, quadratic programming in these forms arise in many applications, and many problems in combinatorial optimization can be formulated in this form. So consequently, this kind of problem will be an NPR problem.
Sorry, Moslem, I think you're having problems with the mic because we cannot hear you well.
Now, it's clearly.
No, I think you are still having the same.
It seems okay. I don't know how to use clearly.
Okay, can you try again?
How do you receive my voice clearly or not?
I think now it's better.
Yeah, I need to change the microphone off.
Yeah, now I can hear you clearly.
Sure.
Okay, good.
Now I can first. Okay, as I mentioned, also it was shown that polynomial optimization problem in general can be reformulated as a quadratic programming in this form. Before compounds, presentations, I will show unit box IB and X stand for the feasible set corresponding to linear constraint, and capital F shows the feasible set of QP. However, we show quadratic and find functions on Rn by QRn and ARn, and show non-negative and quadratic function by a plus x and plus x. Also, we show non-negative convex quadratic function on x by q plus c of x. It's known that a quadratic function is non-negative on Rn if and only if we have this quality. I mean that this matrix must be a semi-positive difference. Most common bounds for optimization problems is obtained by using Lagrangian dual. In fact, for the QP, the Lagrangian dual can be formulated as follows. Here, Lagrangian variables are real numbers. One important question that arises about this formulation: how one can improve this bound? As you know, common method for improving SOS polynomial as a Lagrange multipliers. So if place here beta I, gamma I, and lambda I, and Q plus Rn by sum of square polynomials, we will obtain Lasser hierarchy. So before we move into the second level of Lasser hierarchy, because first level is equivalent to the Lagrangian duality, we may take advantage of the structure of problems and using another polynomials to improve the Lagrangian bound. Length, worth mentioning that dual of Lagrangian dual is well-known semi-definite relaxations. Semi-definite relaxations for the quadratic program, that is exactly the dual of this problem, can be formulated in this form.
Sorry again, Moslem. We're again not hearing you well. Maybe you can get closer to the microphone or something like that.
Moslem, maybe the problem is you should change the microphone setting. You know, in the do you see the mute in the left bottom side? There is an option. You can change the microphone.
I change it. What now? You hear me?
I can hear you, but it's a little bit broke. So
okay. Could you hear me now?
Now I can hear you. Yes.
Yeah. I had three options. I try all of them. Just one of them works. That unfortunately cannot hear my voice. What's the problem? The hardware of this laptop doesn't compatible with Cisco. Okay. Shall I continue?
Yes, please go ahead.
Okay. And it's well known that semi-definite relaxation is exact if the solution of these problems has rank of 1. And recently it has shown that semi-definite relaxation always has a solution with rank of at most 2. Point. But these formulations, these problems has a strong feasibility. By strong feasibility, I mean that conic problems will remain feasible with a small perturb right side of constraints. As explained, all of the problems in these presentations satisfy this property. So for all problems here, we have a strong duality. So we return to the Lagrangian duality. Now, to prove the bound, we can place the scalar variable with defined function. For example, here, think beta I as a affine functions. Here, gamma I are affine functions. So, because we need to have a bound for the problems, we need that this beta I and gamma I to be non-negative on the feasible set. So because of that, we consider a subset of Rn that contains our feasible set, and also we can characterize non-negative affine functions in computational way. In fact, in this case, because capital X is a polytope, by using Farkas lemma, one can characterize non-negative affine functions on X. So we obtain these formulations, mentioning that this bound, and by doing some calculation, one can show that this bond is a special case of the bond that is introduced by Lasser and his workers. In fact, in this paper, they introduce a new hierarchy that is a combination of Lasser hierarchy and Handelman hierarchy. And again, it's natural to ask about the dual of these problems. The dual of these problems can be reformulated as follows. Also, this problem is very well known. In fact, this relaxation or semi-definite relaxation is obtained by the combination of the semi-definite relaxation and RLT, formation linear technique. That is used by 2009. And can check it that constraints all comes from RLT method, and last one is the semi-definite relaxation constraint. Also, in the paper, Borer have shown that this bond is exact for any quadratic program if and only if we have two variables, but in general it's not exact. So we obtained a bond, but also this bond is no. Just obtain a dual of this bond, this relaxation. Okay, how one can improve this bond? One method can be changing the ground set. By ground set, here just consider the non-negative quadratic functions on Rn. Because of our formulations, we can replace, for example, here non-negative functions on unit box. By using these formulations, we obtain a new bond as follows. For these formulations, we have a nice property similar to the Borer theorem. One can show that this bond is exact for the case that our variables, some of our variables are binary. Moreover, this problem can be formulated as a copositive program. As you know, copositive program is an NPR problem, so this formulation leads to a problem. All positive notions, a matrix, symmetric matrix of A is called copositive if its bilinear form is non-negative for any non-negative vector of X, and copositive program can be formulated similar to the semi-definite programming. Instead of this constraint that says that X must belongs to the copositive matrix. Now we are going to prove the bond. Now, for this end, we can take advantage of our feasible set. For example, if we have some convex quadratic constraints, we can characterize non-negative affine functions on the set that contains these constraints. So, for example, show that indices of constraint quadratic convex by MC, and also the level set corresponding to the convex constraint of I by Li, and we can formulate a bond this way. This formulation, similar to the former formulations, we have non-negative affine functions plus non-negative affine functions on the level set of I. Level set of I constant. So we obtain these bonds. Again, we are interested to know the dual of this bond. Dual of this bond can be formulated as follows. These formulations, Ri is a matrix that we have this property. Qi is equal to Ri transpose Ri. Also, this bond known in the literature, like it was introduced later in Matborg in 20. And so again, we obtain a bound that is well known, but now we can improve. Here, just consider the case that our affine function is non-negative on the level set of I constraint. Of that, can consider non-negative affine functions on the set that consider all convex quadratic constraint intersection with affine function, affine constraint. In this case, by using some linear matrix inequality, we can characterize all negative affine functions and obtain this new bound. One interesting point about this bound is that by using this bound, we can obtain one extension of S lemma. S lemma says that, or S procedure, for the case that we wanted to minimize a quadratic functions on the level set of a quadratic functions, we have a strong duality if we have a Slater constraint qualification. In fact, these two problems share the same optimal value. By using this bound, if we have a quadratic program that we constraint has two constraints, one is convex quadratic constraints and another one is a linear constraint. Also, we assume that we have a Slater constraint qualification. In this case, we also have a strong duality. I mean that the optimal value of these problems and problem 7 are the same. So, prove the bound. Next bound, we consider some valid constraints for the quadratic program. By using valid constraints, we obtain new bound. By valid constraints, I mean that a constraint or inequality is valid for an optimization if each visible point satisfies the given constraints. Class of valid constraints for the quadratic programming can be obtained by using this. Big omega as a subset that contains our feasible sets and shows the optimal value of linear for the omega for any matrix of S. This quadratic constraint be a valid. So by use of constraints, formulate a new bound. Again, here we take advantage of this valid constraint because they are in fact a convex cone. We add it here and we formulate a new bound. All of this bound fact can semi-definite programming in this form, and also this one is paper by his co-workers. But again, this bound is just here, and they consider formulations. They only consider non-negative point function level set of here non-negative function set of W. That W is the all points that satisfy linear constraints and mixed quadratic constraint, plus U valid constraint that all of them are also quadratic. So we obtain a new bond. And for this bond, cited are all bonds that we mentioned here. You receive my voice clearly because feedback.
Oh, sorry. I can hear you, yes, but a little bit broken, but I can hear you.
Okay, sorry. Okay. Now, next part, I'd like to improve this kind of bond. So far, we're using just affine functions for the Lagrange multipliers. One way to improve this kind of bonds is use polynomials with a degree greater than 1. If we use this method, we obtain a cubic functions. So checking the non-negative function is not easy. In fact, if we consider a cubic Rn x negative value, so we need to limit cubic function on the subset of Rn. The easiest way it can be considered because our physical set is a subset of non-negative orthants, so we consider a cubic functions with non-negative coefficients. That easily seen that this kind of cubics are the non-negative. So by using these methods, now we replace for the quadratics, replace Lagrange multipliers by affine functions. For quadratics, for linears, we're using quadratic function as a multiplier. So we obtain these formulations. Another point that is important about using this kind of bond, because each time we obtain quadratic functions by solving these problems, that is provide a convex lower estimation of our objective function. So it can be used as lower estimations and can generate a point for for example, branch and bond method. In fact, I use this method for proposing a method for solving quadratic program. So we obtain cubic bond. Cubic bond is not very common. Quadratic program. Rest of my knowledge, because I was interested to check the equivalence of this bond with other bonds. I found it just one bond that is have same number of variables for quadratic program. It's obtained, it's introduced for the standard quadratic program. Standard quadratic program even as a minimization of homogeneous convex function on a standard simplex. As you know, finding the clique of a graph can be formulated as a standard quadratic program. So this problem is NP-hard. Solving these problems, parallel hierarchy. Parallel hierarchy check a compositive of a method. We check that this polynomial is sum of a square or not. This method, because here R is the natural numbers, the convex cone of PR, which defines as follows. Example A belongs to the PR if its polynomial is sum of a square. Standard quadratic program by using parallel hierarchy can formulate this form. First level, take it, solving these problems, you will obtain a lower bound for the standard quadratic program. So it may be of interest. Compare the given bonds with the bond that obtains by using parallel hierarchy. In fact, that for a standard quadratic program, that I introduced is equivalent to the Pareto hierarchy with order of 1. And the last bound that I introduced is equivalent to the Pareto hierarchy with order of 2. Of course, mentioning that all of them have almost same number of variables. One may interested how to extend this kind of method. One way to extend this method can be using this kind of idea. For example, for the Lagrange multipliers, instead of we can check it. For example, we are interested using X transpose Q hat X plus 2 at transpose X plus C0 as a Lagrange multiplier. So we need to check the non-negativity of these quadratic functions. One way can be checking the non-negativity of these quadratic functions by the one that is given. Also, any Lagrange multiplier here can be checked in this way. We check that the system is consistent or not. That this idea with hierarchy, but I don't know, this kind of hierarchy is equivalent to some well-known hierarchy in the literature or not, but of interest. And last slide, taking different bounds from the computation. In fact, I compared two bounds, the first one and the last one. I generated 26 random quadratic problems, 20 decision variables with 5 non-convex quadratics, quality constant. In this figure, y-axis shows the difference, the optimal value, the given bound. As you see, the cubic bound provide a tighter than bound. In fact, in some cases, exact, it can exact. But from the computational point of view, on average, it takes a 0.1 second to compute quadratic bound, but for the cubic bound, it takes a 3.8 second to compute the cubic bound. So, can infer that from computational point of view, cubic bound is not very practical. Okay. If you are interested, bounds you can find proofs and papers.
Okay. Thank you, Moslem. So I think we have time for questions now. So I do actually have a question here, Moslem, and it's how do you compute the optimal values in this plot here, in this experiment?
Because each bound can be formulated as a semi-definite programming. In fact, I used YALMIP to compute the bounds for problems.
Okay, but you are showing us the gap, and you said that sometimes you get the optimal value.
Yeah. Because in fact, to obtain the optimal value, I used Baron.
Okay.
Obtain the optimal value and take the gap between the optimal value and generated lower bound.
So this is the gap between your bound and Baron.
Yes.
So in some cases, it might happen that Baron doesn't compute the optimal value. Or
yes, because here I use Baron to obtain the exact optimal value.
Okay.
After that, I check the difference between the generated lower bound and the exact optimal value.
Okay. Okay, good. Thank you. Do we have more questions? I have another one, and it's about your compositive reformulation. So when you do the compositive reformulation in the case of binary variables, how does that relate to Euler's?
In fact, we're using the same method for proving this one.
Okay.
Idea is same. Because of that, I mentioned the prover for this problem.
Okay. Okay. Okay, I don't see more questions. Okay. So I will thank Moslem, and again, I will take David for the nice talks today. And I think now we have a break. And then after that, there will be let me just check in there will be or maybe Etienne can say more because yeah. So at 4:30.
Yes. So there is an exercise class planned for 4:30. So for those who still have stamina, so we can discuss some exercises from the slides of the tutorial today.